Sounds good. So thanks for the introduction. So I will give an overview of what is ongoing on the R&D for next generation of energy physics collider calorimeters, experiments in calorimetry. And clearly there's a broad landscape, not just in terms of applications for different colliders, but also on the technology. So this is of course, a biased overview, and I will balance maybe previous talk because I will have some pictures from CMS more than Atlas, but I will try to pick a few examples that kind of illustrate what are the general trends in the R&D. And now, clearly, a calorimeter in principle is a very simple thing. So what you do is that you just absorb entirely particles, you fully stop them, and you convert their energy into an electric signal, and what you get out is the measurement of the energy. This conversion can happen in different ways depending on technology. You can, as we have seen in previous talk, use silicon ionization in silicon or in gases, or you can use a generation of light. Now, in reality, there's a lot of more complications when you need to design a calorimeter, because in the end, you need to deliver it. So you start from basic principles to design it and optimize it, but you need to think of how you actually build it and integrate it and all that kind of thing. So those are really, for what a calorimeter is really sort of a big system, and these are really important aspects when you need to design it. Now, let's start from where we are now and what are the drivers of the R&D at the moment. As you know, calorimeters are a central part of a detector at energy physics experiments, because they are devoted to the measurement of energy, of electrons, positrons, charged hadrons, but those can also in some sense be measured, their momentum can be measured by the trackers. What cannot be measured by the trackers and has to be necessarily measured by the calorimeters are the neutrals, so photons and neutral hadrons. And historically, or let's say most of the detector experiments, the calorimeters are divided in two sections, one for electromagnetic particles, electromagnetic calorimeter, ECAL, and one for hadronic hadrons, hadronic particles, HCALs, the so-called HCALs. And this is not really necessarily for basic principles, but it's mainly driven by practical reason, because you want to optimize your ECAL in terms of granularity or performance. But since hadron showers, they need much more space to develop and to stop the particles, you cannot afford to scale up the system to the amount of volume that you need to contain hadrons. So this is really why most of the times these two sub-calorimeter are divided in these two sections. And one of the key benchmark when we talk about calorimetry is how well they can measure energy, so energy resolution. And we have seen that for the trackers, the momentum resolution gets worse with the momentum of the particle. With calorimeters, it's the other way around. So the energy resolution improves with energy. This may help you in some cases, so for some specific collider application at higher energy, in some sense. Now, how well this improves with energy and with what behavior, this depends on the sharing of this contribution to the energy resolution, which are often divided into a constant term, which may be anything that doesn't scale with energy. So you have calibration issues, instability of your calorimeter signal or whatever. You have noise, typically from electronics, and this goes down linearly with the 1 over the energy. And then you have a term that goes down with 1 over the square root of energy, which is so-called stochastic term. And you see here in the picture a comparison of what is the energy resolution as a function of energy for different calorimeters at LHC, on CMS, and Atlas, LHCb, and ALICE. And well, differences are in the details, but if you compare the electromagnetic calorimeters, but you can clearly see that there's a big difference between the electromagnetic calorimeters and the hadronic calorimeters. So let me quickly explain you why. For what concerns electromagnetic calorimeters, the sampling term, which is usually assuming you have an electronics that you can control well enough and keep the noise term small, assuming the constant term can also be kept relatively small, within 1% typically, then what the defines, especially at low energy, the performance of a calorimeter is the stochastic term. And this depends mainly by the amount of the electromagnetic shower that is being developed in your calorimeter that you sample. So if you have, you see a calorimeter where the full shower is sampled and it's fully converted into signal, then you don't have any fluctuation because you always detect all the shower. In sampling calorimeters, instead, you alternate layers of active materials with absorbers. So you use a passive absorber to stop the particle, and then use thin active layers to actually measure the fraction of MIPS in those layers. And get an energy signal out of that, which is always proportional to energy, but it's subject to larger fluctuations. And for this reason, you can see here that depending on what's the actual sampling fraction of each electromagnetic calorimeter, the energy resolution degrades linearly with 1 over the square root of the sampling fraction. And you have, when you use silicon, where you have very thin layers, then the sampling fraction is very small, and the electromagnetic energy resolution can be as bad as 25% of a square root of phi in terms of stochastic term. Then you have a sampling calorimeters always based on sampling, but where you have maybe scintillators, and there you get a more higher sampling fraction, and you are usually in the ballpark of 15% of a square root of phi energy resolution down to 10. And then you have homogeneous calorimeters that typically exploits inorganic crystals because they're very dense. So the issue is that you need to do both stopping the particles and converting the signal into light. So you need something that is very dense and that can produce some signal. And that's usually are inorganic scintillators. So yeah, as I said now, beside this sampling term, what's really matters also the electronic noise, calibration, stability, and linearity as important factors. Now, why instead for hadrons and the hadronic calorimeter, the energy resolution is about an order of magnitude worse? The reason is that because of their nature, hadron showers and also jets are very complex objects. For instance, you see here what is the typical composition of a jet, and you have about 50% of the energy of a jet that comes from charged hadrons. And then you have about 30% of the energy that comes from pi zero that generates electromagnetic showers in the calorimeter. So what you have inside your hadron calorimeter is something like this. You can have a large variety of processes that slow down your particle and that deposit energy in the calorimeter. You have some energy is always lost in breaking up nuclei, and that cannot be measured. And then you see you have this sharing between an electromagnetic component of the shower and an hadronic component of the shower. And typically calorimeters, by the way they are designed, they respond differently to these components because the way the different electromagnetic particles interact with your material and convert energy into signal is different for these two components. And since these two fractions fluctuates a lot event by event, you get basically a very large smearing of your energy measurement, and this degrades the energy resolution as well as the energy linearity, because this sharing between the two components of hadronic shower does depend on the hadron energy. So you have two issues, energy resolution and energy linearity, that are strongly degraded. Now, let me, before seeing how these issues can be addressed, give an idea of what are the general trends if you look at R&D for calorimetry. And usually a calorimeter historically were just designed to measure the energy of the particles, but now I think everyone is really moving towards a 6D calorimetry concept, where a calorimeter does not just measure the energy of the particles, but you want to have a very good spatial resolution. So you are boosting the granularity, the segmentation on either both the longitudinal direction and transverse segmentation to levels that can be very, very small. You see here, for instance, this is a crystal of cesium iodide, which is about 5 centimeters square cross section, and you have in the same size you can put instead, this is a spaghetti calorimeter with crystal fibers, and they have 1 by 1 square millimeter. So there's really no limit from the technological point of view to how granular you can go. And we have seen in previous talk that if you use other technologies like silicon or gas detector, you can even go to a finer granularity. Then the other things everyone wants to measure precisely is time. We have seen that there are good reasons to do that for future colliders, but also for high luminosity LHC. And we want to go down to order of 10 picosecond time resolution. This is within reach. This is an example. I mean, a lot of electromagnetic calorimeters can already reach this. At 5 GeV, you see with this spaghetti calorimeter, you get 20 picosecond time resolution for electromagnetic shower. So it's something that is within reach, and is within reach also in some of the upgraded detectors for the luminosity LHC, like in the CMS electromagnetic calorimeter. And then there's also a trend or possibility, let's say, to measure the nature of the shower. So as I've shown before, for hadronic shower, where there's each shower can develop with different fractions of hadronic or electromagnetic components. One can think of a mixture of active materials that are sensitive to different types of the shower, so that you basically have a multi-signal calorimetry with dual or triple readout. Now, technology is such that we can really do wonderful things. On the reconstruction side, the idea is also to move from just an energy measurement to an overall combination of all the information from the calorimeter, the trackers, in what is a particle flow approach, and exploiting the new machine learning techniques. What needs to be defined is what exactly do we need from the experiments, and then how we really can design a collider-tailored calorimeter for that specific applications. We have seen that there are several options on the table from the future circular collider, E plus E minus at CERN, but also the one which is identical and could be built in China, or the muon collider. And you see from the size of these, and of course also linear collider, E plus E minus linear colliders as X factories. But the size of this is really certainly a challenge, a civil engineering challenge. And also the timeline of this project is clearly very long. We have seen we need time to design these colliders and these detectors, as we have done for LHC and luminosity LHC. And all these projects will not start before the end of luminosity LHC. And different timelines. These are in continuous evolution, of course, but the comment I want to make is that there is a now ongoing and intense R&D phase on the detectors, because if you want to R&D, you need to do it now in the next 5+ years, because then you will have to move into really, get to an engineering level design and start to building it, because that as well takes like a decade. And of course, well, it was discussed that it is a challenge, of course, to keep engagement of people and the next generation of physicists into a commitment on this longer time scale. Now, what are the requirements for the calorimeters that come from different collider options? You see here a qualitative representation of how different colliders pull your R&D towards different directions. And we have clearly the first collider, next collider is luminosity LHC. And this is already setting quite some challenges in terms of radiation tolerance. We had to replace a lot of our detectors to deal with the expected radiation levels, and also to deal with the high level of pileup that we expected at luminosity LHC. And this was partially used by the introduction of timing in our detectors. We dedicate in the calorimeters, but also with dedicated timing detectors. And you can imagine that a future circular collider with hadrons, with protons, after the E plus E minus phase would push this even farther in all of this direction. Like it's going to be like 10 times tougher on all these aspects than high luminosity LHC. On the other hand, the E plus minus colliders, they do not have the same radiation levels or pileup, so there's much cleaner environment. So you can not worry about that, or not worry much about that, and look for really doing precision measurements, building the best detectors you can to profit from these E plus E minus colliders. Depending on the energy, I'll not talk about this, but you also, if you want to measure very low energy particles or very high energy particles, you also need to have different design and optimization of your calorimeters. And then we have seen broadly this morning what are the the needs from a muon collider in terms of tackling mostly the beam-induced background challenge, as well as non-negligible radiation levels and ambitious time resolution. So this is kind of a cartoon of not all, but a few of the calorimeter designs that are ongoing. I call it a zoo because really there's you can imagine different layouts with different technologies. You have sampling calorimeters based on liquefied noble gases like liquid argon calorimeter from Atlas. You have a family of very high granularity calorimeters based on semiconductors or gaseous detectors. And then you have always sampling calorimeters, but based on scintillators. And these can be both for electromagnetic and hadronic calorimeters. There's a mixture of them. Then you have a family of homogeneous electromagnetic calorimeters. So here, these are the ones you need if you really want to push the electromagnetic energy resolution to the 1-3% of a square root of E level. And you cannot, there's also, say, some proposal for homogeneous calorimeter that can measure both electromagnetic and hadronic particles in an homogeneous way. Of course, if you want to have more details, you can check out Calor 2024 conference. There's really a nice overview of many of these, and there is, we will hear more about it later in the week, a dedicated DRD collaboration that is being was just born at CERN early this year that is targeting R&D on calorimetry. Now, as I said, a fraction of these calorimeters, they use we call them optical calorimeters, so they can group into this family because they convert the energy of the particles into a light signal, usually using either organic or inorganic scintillators. Sometimes they use wavelength shifters to change the wavelength of the light to what you need. These are these pink things you see here. And at the end, you need to detect this light with some photodetectors. And I think in all of these designs, now the trend is to use silicon photomultipliers. So this is really the next generation of photodetectors that is being broadly used. They are insensitive to magnetic field. They're very compact. They operate at low voltage with respect to other photodetectors, and they also are very cost effective. So there's a lot of synergies on these technologies for all of these calorimeters. And then there's another challenge that is common to other families of calorimeters. We call them sandwich calorimeters, where you are really pushing for an extreme longitudinal segmentation, like you want to have in an electromagnetic calorimeter. Instead of single layer, you want to have 20 layers of longitudinal segmentation. But then you need to include in each layer not just the active element, but also the readout electronics. So you have sandwiches of like silicon sensors, the PCB with electronics, and the absorber. And you see the challenge here is that in each layer you need to have the to have your electronics, your signal, your service routing. You have to cool down the electronics and the detector. So you want some sense to miniaturize that, and this is common to all these calorimeters that have a very strong longitudinal segmentation. Now, the way I will walk you through this zoo of calorimeter is by looking at some of the challenges that are trying to address. Clearly, each calorimeter can be really, it was born for with a specific collider in mind, but it can be easily moved to application to another collider with minor modifications. So don't think them as calorimeters for a single collider, but there's really, at this time, as of today, there's really a possibility to design everything and move one calorimeter to another collider with few changes. So I will talk about, I will bring you a few examples on how the challenge of pushing further the energy resolution of jets is being addressed, and this is of much interest for FCCE applications. I will say a few words on the challenge of beam-induced background challenge from muon collider, and then another big challenge, which is the radiation tolerance and pushing this frontier really to another order of magnitude for future FCCHH. And then I concluded a few remarks on some exotic R&D that is going on. So concerning jet energy resolution, the reason why this is a benchmark for the performance of a calorimeter is that at an E plus minus X factor, the X production is mainly through X Strahlung, and what you end up with is that the vast majority of your events is going to have a final state with many jets, like 30% with 2 jets, 55% with 4 jets, 11% with 6 jets. So when you have many jets in the calorimeter, jets is usually reconstructed by pulling together all the particles within a cone. You can imagine that this is becoming challenging, because you can have overlaps between these cones. And what is a usual target for this jet energy resolution is that you would like to be able to divide or separate dijet decays of a W boson from those of a Z boson. So for that, you need an energy resolution for a jet at that energy of about 3 to 4% there, which means about 30% over square root of E energy of your calorimeter for jets. Now, the issue is that state-of-the-art jet energy resolution at LHC is like 2-3 times worse than that, and mostly because the hadronic calorimeters that are being used in these experiments have a poor energy resolution. So how this can be improved to this level of the resolution that we need? There are historically 2 approaches to tackle this challenge. They've been seen as 2 separate approaches in the community for a long time, but I think this is changing now. One is so-called particle flow. So the idea is that the problem is always that you have these fluctuations between the hadronic part and the electromagnetic fraction of the shower. And what you want to do with particle flow is that those 55% of the jet energy that comes from charged hadrons, you don't measure it using the calorimeter. You measure it using the tracker. So for all the charged particles, instead of using the calorimeter, you use the measurement from the tracker, which is much more precise. But then you need to take out those energy deposits inside the calorimeter of those tracks that you're measuring with the tracker from your calorimeter. So you don't count them. You just need to count from the calorimeter the energy deposits that come from neutral particles, so photons and neutral hadrons. So you need to be able to do this separation of the heats of energy deposits inside your calorimeter by matching them with the tracks that you have. And to do that, clearly an handle that you need is to have a very high granularity on longitudinally and fine segmentation on the transverse direction so that you can have a good matching. The other approach is instead very different. What you want to do is that you want to measure on an event-by-event basis how much electromagnetic fraction of the shower there was and how much of the hadronic shower in the jet was there. And to do that, you can think of a calorimeter that has 2 different active materials. One is more sensitive to the electromagnetic fraction of the shower and one to the hadronic fraction of the shower. And by measuring event by event how this ratio of these 2 active component signals, like scintillating fibers and Cherenkov fibers, you can apply a correction event by event, and you can see that you can restore basically with this correction the response of your calorimeter to be a linear response and with a better energy resolution. One way to do this is that you use a Cherenkov sensitive material, or you measure a Cherenkov signal, and since the electromagnetic fraction of the shower has more relativistic particle, like the light electrons, you have a higher Cherenkov signal. Okay, so if you have a higher Cherenkov signal, it means that your hadron shower jet was containing more electromagnetic component of the shower than the hadronic one. Now, concerning the first approach, as I said, granularity is more important than energy resolution. These are some senses kind of could sound weird for a calorimeter, but that's the case because you're not going to use the calorimeter for the measurement of the charged hadrons anymore. You need the good lateral granularity at the level of that should be smaller than your Molière radius. So you should be, the shower has an intrinsic transverse width. You want to have the cell of your calorimeters to be smaller than that. And you want to have a dense absorber so that the shower also stays as small as possible in space and doesn't spread or broadens up into your calorimeter. And this, of course, you see here, for instance, an example of how in about 20 layers of an electromagnetic calorimeter this is from CMS AGCAL, you see the shower development, and the same for a 300 GeV hadron. you can really track what's happening and how is the hadronic shower development. When does a pi zero starts an electromagnetic shower and so on. And now, as I said, for a calorimeter, calibration is important. So you need to be, if you have such a calorimeter with a large amount of channels, you need to be able to calibrate them. So ideally, you need to have a sensitivity to the single MIP so that you can use that to calibrate all your cells. How do you actually implement this? You can have different approaches. One is to use plastic scintillator tiles. So you can have tiles of plastic scintillators as small as a few centimeters or as large as a few tenths of centimeters square, or even strips. So you can really think of different ideas on how to optimize it. And these are read out. You see there's a little kind of carved dome inside the plastic scintillator where you can place your silicon photomultiplier, which is this one very small, and then you wrap all your scintillator with some reflective material to optimize the light collection efficiency, and you attach this tile onto your PCB, and then you see you have the electronics and the cold plate. This procedure is also being automated, this wrapping and assembly, because you need a lot of channels, and it's being used. This was there was a lot of development within the Callis collaboration, and this technique is being adopted also to instrument a fraction of the CMS high granularity calorimeter for the luminosity HHC upgrade. Now you could, as I said, instead of using plastic scintillators, you could use semiconductors. One advantage is that they're more radiation hard than plastic scintillators. So for instance, in the CMS high granularity calorimeter, they're used in the region where you have a higher radiation level. This also capitalized over decades of R&D within the Callis collaboration. And just to give you an idea of what's here, what you see is a wafer. This is 6 inches wide. They call it high definition because the cell has a size of half to 1 centimeter hexagonal dimensions. That is what you have. And in total, to give an example of what the CMS high granularity calorimeter has, is 6 million channels and 600 meters square of silicon. So that's more than a tracker, because of course you're moving out from the interaction point, the volume becomes bigger, and you have 24 layers for the electromagnetic calorimeter and 21 longitudinal layers for the hadronic calorimeters. And now, as I anticipated, the real challenge is that you need to have this stack up of sandwich of these different layers. And in each layer, you need to have all these services, provide the power to the sensor, take out the power that is dissipated with some cooling system and so on. So that's really kind of challenging. You could conceptually think of further boosting the granularity, and we talk about a boost of 10 to the 4. So you go from like square centimeter level cell size to 100 micron size, using like we have seen in the previous talk CMOS maps. And again, you are using a different technology, but the idea is always that you have you stop the particles with a dense absorber, and then you have some semiconductor material that measure your MIPS. Now, what happens is that with this huge amount of channels, also the occupancy of MIPS per channel gets smaller. You actually may not need to measure a signal that is proportional to the number of MIPS, but you go fully digital. So you just get a 1-bit resolution. So either you had a signal or not into that pixel. And the way you reconstruct energy, because we're not a tracker, we need to reconstruct energies, that you just sum up all the number of hits you get, and the more hits you get, it means the more MIPS you add, and you reconstruct the energy. Now, clearly there's R&D, there's a technological challenge in getting a very low power consumption from these devices, as we've seen in the previous talk, and the challenge on how to deal with all these channels and how to optimize the reconstruction by clustering the cells. So this what you have here is like an ideal performance, and this is where we are with some clustering algorithm at the moment. Now, as I said, the other approach to address the jet energy solution is to use dual readout calorimetry. Here, what you do is that, as you said, you use different materials to have measure a proxy of the fraction of electromagnetic shower that your hadron is making into the detector, and then you apply, you know what is the performance of your detector to hadrons and electromagnetic particles, and with those coefficients you can calculate a correcting factor that you apply to the energy, and you get back the linearity. You could separate Cherenkov and scintillation with different active materials, or you can do that based on timing, because Cherenkov is a very prompt emission, while scintillators, they may have a slower scintillation signaling time. So you can also just think of measuring in two different gates the signal you get, and that's a way to use the same active medium to measure these two Cherenkov and scintillation component. The way you implement this also dates back to a very long-standing R&D and prototyping and proof of principle from the DREAM collaboration, now to new prototypes that are being built, like the Hydra prototype. This is how they all look like, more or less. You can have different flavors, but in the end you have a groove of an absorber, and in which you feel all these like 1 millimeter fibers, and you see here the blue ones are for Cherenkov, the yellow for scintillation. And then you read out, you can group, you can either go to a single fiber readout enabled by the silicon photomultiplier, so you can imagine a single photodetectors for each fiber, or you can group them to whatever granularity your detector needs in the end. Now, jet energy resolution is not the only benchmark for calorimeter, because you can imagine that there are other physics studies that cases where you would like to have an energy resolution for electromagnetic particles, and in particular photons that maybe comes from the case of pi zeros, that requires an energy resolution at the level of 3%. So for instance, in some CP violation study with the BSDK, you see that a resolution of 15% of a square root of phi for pi zeros does not allow you to make a reasonable data analysis, while a 3% of a square root of phi can really make a difference. And you can also imagine that if you have a very good resolution to pi zeros, you can cluster the photons that are coming from the pi zeros before applying your jet clustering algorithm. That's also something useful. And you can have, if you have a very good electromagnetic resolution, you can even recover the performance of the recoil mass from the Z into 2 electrons to the same level of the muons by recovering the photons from Bremsstrahlung that are emitted by the electrons. So how can you get to this level of resolution for the electromagnetic part of the calorimeter? Well, you need to have an homogeneous calorimeter, but at the same time, as I said, we're going towards a 6D calorimetry. So what we also want is granularity. And this is an example of a calorimeter design. We call it high granularity crystal calorimeter, mostly developed for the CEPC collider in China. And you have crystal bars that are arranged in a grid like this, and you stack many layers of this. And that provides you a very high level of spatial granularity while keeping a basically fully homogeneous calorimeter. So and there's really a huge work on the level of reconstruction algorithm with dedicated particle flow algorithm. Another approach is always using a homogeneous calorimeter, but as I said, inside your homogeneous calorimeter, you also include the capability to measure the electromagnetic fraction of hadrons. Because if you just put an homogeneous electromagnetic calorimeter made of crystals in front of your dual readout calorimeter, then you have a fraction of hadrons that deposit energy in the ECAL that you don't know how to reconstruct unless you measure let's say, a dual readout signal also in the crystal calorimeter. And this is another idea that can be implemented so that you don't have anymore a single monolithic dual readout calorimeter, but you segment it and you have an homogeneous section at the beginning and the sampling fraction in the back. And if both sections have dual readout capabilities, that you can still have a pretty performant, a good performance for jet energy reconstruction. Now, so this is to say that while historically these two approaches to reconstruct jets were kind of seen as separate, I believe that there's no real reason to see that as anymore, because one can really, with the technology we have, one can think of going to high granularity and use particle flow algorithms, but at the same time use a multi-signal calorimeter type, so that you can also use both techniques together. And this is something one can think about. You see, you can the flavors of your calorimeters can really span in terms of granularity and energy resolution, but there's really a chance to get something that is performant on both aspects. Now, a few words on the beam-induced background challenge. So we've seen that a lot in the previous talk about what this is. Now, what is the strategy for the calorimeter to mitigate that? High granularity, because as we have seen, being at low energies, you can really, if you have a longitudinal segmentation, you can really just see that the bib particles just deposit energy in the first cells of your calorimeter. Excellent timing, because we have seen that they're mostly, a lot of them are out of time. So if you have a timing at level of 100 picoseconds or so, you can really take them out from your signal reconstruction. And still you need an energy resolution at the level of 10% over square root of E. And we have seen in lowest talk that the baseline is a silicon tungsten ECAL, because as we have seen in previous slides, this gives you a very high granularity. But so what I talk about instead is another option that is under study that has less channels, but may also be advantages from other aspects, so complementary. And is based on segmented crystals. So this is they call it crystal calorimeter with longitudinal information, krillin, and it's divided like in 5 longitudinal layers, and each layers you get silicon photomultipliers with electronics readout. So it's basically a homogeneous calorimeter. It can give you a good energy resolution for electromagnetic particles, and the time resolution at the level of 100 picosecond for energies. You see, you have 58 picosecond over energy in GeV. So that's for low energy, you still have a pretty good time resolution. And the crystals that are being considered are lead tungsten, an ultra-fast version of this lead tungsten crystal that has a long history for application in calorimeter, but this is optimized for a very fast response, or lead fluoride crystal that are also very fast. Now, for the hadron calorimeter as well, another option that is under consideration for the muon collider is to use micron pattern gas detectors. So again, we've seen a few words on how they work in previous slides, but basically you exploit the ionization of a gas to generate some charge. Then this charge is amplified in a high voltage region, and then you collect this amplified charge at an electrode. And you can have by having these structures of the electrodes, you can have a very good granularity. And both transversally, but also longitudinally, because you stack up these layers of again of MPGD active materials with your electronics and your absorb. And the key features is that they can operate at a high rate, which is necessary for a muon collider, and they are additional in some sense intrinsically, because the gas doesn't get damaged from that. And there are various technology on the table. There's again detailed optimizations, but they're all first studies indicated they can all operate well and give a reasonable efficiency for measuring what you need. Now getting to the FCC-HH, so the challenge of radiation levels and also pile up, because they come usually together. We can think that the high luminosity LHC is like 5 to 10 times worse than LHC. And imagine that FCC-HH is again another 10 times worse than high luminosity LHC. So, I mean, we've been struggling to get the detectors working for high luminosity LHC with the upgrades that are ongoing now. And it's kind of hard to think of another step of a factor 10. But what are these challenges? So pile up means that we get per bunch crossing. At high luminosity LHC, we are looking for something around 200, maybe a bit lower. We've seen a few in the talk from Beniamino yesterday. And for the high FCC-HH, this is going up to about a pile up of average number of interaction per bunch crossing, which is equal to 1,000. So you see that the distance between the vertices inside the same bunch crossing gets reduced a lot. So what already was a strategy for high luminosity LHC was to exploit timing. So they are very close in space, but they have also some spread in time because of the way the time it takes for the two bunches to cross with each other. This is about 3 picoseconds in high luminosity LHC. And this is gonna get down to 0.4 picosecond in time at FCCHH. So clearly timing helps, timing in the trackers. We heard something in the previous talk. As of today, the CMS and Atlas are implementing dedicated timing detectors to reconstruct the tracks. This is some are using low gain avalanche diodes for the end cap region where the radiation level is higher, and for the barrel region of CMS, crystals and the SIPMs are being used. And what you can get is the time resolution at the level of 30 picosecond. Now imagine you need to, if you want to really tackle this challenge at FCCHH with the same strategy, you need to get below 10 picosecond would be advisable. So now this is for the tracker, but to reconstruct the tracks, but you also want to have this feature of timing in the calorimeters, because you can imagine you get also a lot of spurious energy deposits in your calorimetric cells, and it gets difficult to isolate the energy deposits that becomes from the particles you want to reconstruct in jets, but also in electrons and other particles. When you cluster the energy deposits, you want to get rid of those that are like coming from not the primary vertex, so to remove pileup. And to do that, if you want to reduce this pileup by a factor of 5, you need to have a 25 picosecond time resolution, and by a factor of 25 picosecond. So this is not too far from the state of the art, but so probably the challenge is not getting to this level of time resolution, but doing that in the very high radiation environment. And this is to give you an idea of what is the radiation environment. So maybe the number, again, it's 10 times more than what we will have at the end of high luminosity LHC. We have about 10 to the 16 1 MeV neutron equivalent per square centimeter. This quantity is used to quantify the damage in silicon, because it was found that this damage in silicon is mainly proportional to this type of radiation equivalent parameter. And so this is really something hard to tackle, and imagine in the forward calorimeter this can go up to 10 to the 18. So you really need to think of something and do R&D in that direction. Now, all the technologies I've shown so far, so the silicon, but also the scintillators and the photodetectors will have a very hard time surviving that. There is R&D ongoing. I will not discuss it here, but so R&D should be continued. But at the moment, the baseline calorimeter technology that is being considered is using noble liquid gases, so like liquid argon, so like for the capitalizing the experience from the Atlas liquid argon calorimeter. Mostly you have they call it accordion structure of absorber material like stainless copper, stainless steel, and in between you have your noble liquid like liquid argon. You get ionization inside this liquid, and you collect the charge at the electrodes. So because of the intrinsic radiation tolerance of the material, this is a promising technology for application in a very high radiation environment. Another option to get denser and again with the idea to keep the showers more smaller in space and more contained, to be able to separate them better. Options are to use liquid krypton and combine with a heavier absorber like tungsten mixed with copper. And there is a dedicated R&D ongoing for FCC within the Allegro detector concept that is looking at how we can further boost this technology in both of energy resolution but also segmentation for application at FCCHH. So let me conclude that FCCHH is very challenging, but we still have some time to tackle those challenges. So I just want to conclude with some few examples of other R&D that is going on. And one is R&D for it's high sampling electromagnetic calorimeter called Granita. This promises energy resolution for electromagnetic particle at the level of 1 to 2%. So like the same resolution of a homogeneous crystal, but it plans to do that using grains of heavy inorganic scintillators like zinc tungstate or BGO, smashed down to like 1 millimeter grains, and then you put all of them together, you immerse them in some sort of liquid, and you have these wavelength shifting fibers. So you get the light is generated inside your inorganic crystals, grains. it is then captured by your wavelength shifting fibers that wavelength shift, so increase the wavelength of your light and take it out, and then you put silicon photomultipliers there. So this is as the potential advantage that you to be much cheaper, have the same performance of a crystal calorimeter, but at a competitive cost, because you don't need the extreme quality of the crystal, for instance, the transparency, and you can produce it in smaller pieces or other production methods that are cheaper than a fully bulk crystals. Another calorimeter that someone is looking into is called chromatic calorimeter. So again, this is promises the same energy resolution of homogeneous calorimeter. So you don't have an absorber, you just have all sensitive elements, and you don't have a physical segmentation with photodetectors. I'm done. But what you do is that you basically virtually segment the calorimeter longitudinally by having different wavelength of the light emitted, so that by reconstructing and measuring at the end what is the distribution of wavelength that you have, you can also infer on what was the longitudinal development of the shower. And last but not least, this chromatic calorimeter, but also other calorimeter, like for sampling calorimeters, are really looking into the quantum technology domain. So you have nanocrystals, also called quantum dots, that have the advantage that you can really tune they are very fast, like less than 1 nanosecond decay time, and you can really tune the emission wavelength depending on the dot size. So this is really something you can engineer. There are of course challenges on how you actually integrate these quantum dots into a calorimeter, but there's some work there. So what I wanted to give was just an overview of the fact that there's a broad and active community on calorimeter R&D, and I think the technology is already at the level that we can, at least for FCC-EE, reach the physics goal that we need, while we have major challenges that need to be addressed for a muon collider FCC-HH, but we do have a longer time scale for that. But also I would like to remind that the real challenge in the end is that one needs to deliver the calorimeter and deliver it on time, and so the challenge is to move from small prototypes to large-scale system, and there you cannot forget about these aspects, from integration to cost, services, and so on. So that's it.
Ask questions.
Ready for lunch.
Thanks for the talk. I'm really sorry for this extremely basic question, but why do electrons create showers and muons just propagate through matter? Like if they have the same energy, why is this difference?
You mean the difference of why muon does not create a shower?
Yeah, why you just have ionization losses for muon, and for electron you have this hard process of creating a shower?
Yeah, it boils down to interaction of particles with matter. So the electron starts to has a higher chances to basically radiate the photons, and then this creates pairs of electron positons. So you create this shower and quickly deposit the energy. Because of its higher mass, the muon does not interact in the same amount of space. So it would need much.
But I mean, they both interact electromagnetically, so I just don't feel the difference between them. The mass is different, but if you just throw like 100 GeV particle, why would mass matter?
Yeah, that's a good question, but I'm sure someone here can answer that. So in textbooks, I mean, if you calculate what's the interaction length for an electron, you see that even accounting for a different energy, like from 1 to 100 GeV, you don't get the same interaction length that you have for an electron. You don't get the same for a muon. So that's why you don't stop them even in an hadronic calorimeter. Yeah.
Radiation length.
I think it was when I was still, electrons, you can contain them, even if you go to 100, 200 GeV, you can still contain them well. But yeah, I think the mass is, if you do the calculation, that should add up.
Okay, thank you.
I think if you thought about it in in like the center of mass frame of the interaction, it might help a little bit because then the mass of the particle matters a lot for thinking about how they. Yes, that's true. Yeah, that's true. You're right. I don't know. I'm.
Muon showers, like in that Maya science cover or whatever. There's a muon showering in that because of a radiated photon. So it does happen. Yes, exactly. So but it's suppressed and it's different, but it's not like it doesn't happen in some way.
Yeah. Do you have an intuitive explanation for suppression?
It's what they said.
Well, I think the question is why does that go as 1/m?
Why?
Yeah.
It's because there's an alpha.
We wanna-
We don't even.
No. Okay. All right.
Electron.
Yeah. Okay.
We can address it.